So the second step that I'd recommend with these problems is to set your z-axis direction. And well, maybe even before that, set your z-datum. Okay. I see a lot of students in this class who are tempted to set the datum at the top of the fluid. And I really recommend not doing that. Recall that in all of our derivations that led up to this, we talk about how pressure increases with depth, or at least for our hydrostatic pressure derivation, we talk about how pressure increases with depth, and we made that derivation of the datum lower in fluid. You can solve these problems with the datum at the surface of the fluid. It just starts to get a little bit tricky to track your negative signs that they created in that example. So I would recommend setting the datum towards the bottom of the fluid and set it based on the information that's provided to you. So in this example, imagine you're given a height h. Right? So in that case, it would be convenient to set a datum at the sort of lower point of that height h, right? Because we don't know the distance from the floor to the center line of the pipe. You're given the distance between the center line and the elevation of the top of the tank, which is the essentially driving force for this fluid flow. Okay. And then 3, set the positive z direction. The examples solved in the book, and I think what makes the most sense is to call up the positive z direction. Okay. So if we were to apply our Bernoulli equation, right, we have E1 plus 1/2 rho V1 squared plus gamma Z1 equals P2 plus 1/2 rho V2 squared plus gamma Z2. Okay, so that's our, we're invoking Bernoulli equation across the streamline from point 1 to point 2. I think as you work these problems, you'll get better at this, just like you do with manometer questions. You can probably immediately see what cancels out. But I always like to start at the beginning, sort of think through what your problem is telling you and what you set out. So we have a sort of nasty looking equation with 6 terms, but what can we simplify about it? Let's start with point 1. What do we know about point 1?
That's 0 height.
Sorry?
Is that 0 height?
Point 1 is at the top of the fluid.
Number 2.
Number 2, so yeah, you're right. Z2, because of where we drew our datum, that's equal to 0. But for point 1, what do we know about the pressure at the free surface?
Atmospheric pressure.
Atmospheric, right? So we'll solve these problems, gauge pressure to make our lives easy, and we can call that 0. It's like 0 gauge pressure. Okay? So I'm adding assumptions and information here. If we were to say this is a large tank, you see those words like large tank or very large tank, that tells you something about what we can assume in our Bernoulli application. What do you think it is? At point 1, if we have a very large tank, what does it imply about our system?
Steady flow.
Yeah, steady flow, right? So that means we have a really big area, cross-sectional area at 1, and we have a really big volume of water. And when we say big, we mean that relative to the cross-sectional area at 2, and the amount of water being taken out at 2.
So
The velocity at point 1 is 0. That doesn't mean the velocity at point 2 is 0, which you have to realize that this is a simplifying assumption. It is not literally explicitly physically true, right? Even for the largest lake and the smallest flow, you could be really nitpicky and calculate how much your water bottle is dropping the elevation of that lake, right? But for the purposes of math, it's in the noise, right? That's what we're assuming with these types of problems. Okay.
Quick question.
Yeah.
So we assume that the stream is or the velocity, but do we assume that the z is also constant for that point 1?
What do you think would happen if we made that assumption?
Then the first portion will be 0, and it's not correct.
Or which first portion?
The lambda or, yeah, that
This?
is, yep.
So if what we're saying is that there's so much water that the HDT is equal to 0, the rate of change of H with respect to time is 0, which was one of our mathematical expressions of how we're calling that portion of the fluid steady state. If the HDT is 0, what does that tell us about H? It's constant, right? So it's not 0, the HDT is 0, but H has a value that is constant that is given to us. Okay, an important distinction. Okay. So the velocity is 0, right, because of the large tank. And then gamma is Z1, not 0. Z1 is equal to H. Okay. Right, so that makes our lives quite a bit easier. So what about here on the right-hand side? What can we simplify?
Would you call the P2 like a dynamic pressure or something?
Say that one more time.
Would you call pressure at point 2 like a dynamic pressure from our previous page?
The pressure at point 2, so the dynamic pressure is 0.5 rho v squared.
Yeah, is that what we call point 2? Pressure at 2?
So P2 is the static pressure at point 2,
Okay.
right? So the dynamic pressure is this term right here.
Okay.
So the dynamic pressure is non-zero,
Okay.
right? We have fluid moving out of here. We've drawn this point at the exit of the nozzle. So that's a typical sort of convenient point that you'll take. If you have a nozzle and you're told that it's flowing open to the atmosphere, I'd suggest you drop a point right at that exit of the nozzle. Because at that point, your fluid has entered an unconfined space. It's an unconfined flow. And you can take its static pressure to be exactly 0. Right.
Otherwise, would we have to have like something there to measure pressure?
Yeah, exactly. Or you might be given it, or you might be asked to solve for it. But if you were, and so we have an example of this in the next lecture. But imagine we were to push point 2 back up here, right? Or you were to not be told that this pipe has an opening, and you're just told to solve for the pressure somewhere in that pipe, right? Then we can't neglect the static pressure at point 2. And I think we can do an example like that in the next set of lecture slides. Okay, what about, so we know V2 is not equal to 0. Typically that's what you'll be asked to solve. Let's just say instead of not equal to 0, let's say it's equal to some number that we don't know. And then what about Z2?
0.
0, right? And that's because we set our datum in a way that's convenient. If you were to have set the datum at the floor, that's often a place that that will be convenient. In an example where instead of being given H, you were given this and this, if you were given Z1 and Z2, both of those terms wouldn't be 0, but what's Z1 minus Z2? It was what we just had as H, right? So it's the same thing. So, there's a lot of flexibility in how you solve these problems and doing what makes sense to you. It sort of depends on, you make your life a lot easier if you think ahead a little bit about what information is being presented to you in the problem, and that dictates or can really make one solution approach a lot easier and sort of prevent you from having to go back and rewrite your equation or erase some terms, right? So let's stick with the initial problem example where we were given H, the distance between the center line of that pipe and the surface. Okay, so this actually simplifies to a pretty straightforward equation. It's one that you'll use numerous times throughout this course, or at least these chapters. So that's work out this math, that's what this simplifies to. And we want to simplify this even further. What's gamma over density? We know a specific weight is, how does specific weight relate to
Gravity.
density? Gravity, yeah, exactly. So if we were to just simply rearrange this for density, specific weight over density, that equals to gravity. So this simplifies to V equals the square root of 2GH. So this is sort of famous fluid mechanics equation from this, relatively complex initial equation that describes a real physical flow. You can, to a pretty good approximation, describe the velocity leaving that flow, or that tank, simply as a function of constants and the height. Okay. All right, so let's look quickly at a few other examples. These are types of problems that you'll encounter. This relates to the question that was asked a moment ago about the sort of potential for double pound pressure and elevation. You might get combinations of manometry and fluid dynamics now that we know something about how to describe pressure velocities in moving fluids. We can combine that with what we learned about manometry piezometers to sort of evaluate real devices that are used to measure fluid flows. So you might be given an example where you have what's called a Venturi constriction. And you might be told something about the nature of the flow moving through this. And then you might also be given piezometer elevations. Right? And you might be asked to solve for Q or solve for delta H, given certain information about the problem. Does this premise make sense to everyone? We have a flowing tube, flow flowing through a tube with two piezometers attached at the larger diameter portion of the tube and the smaller diameter portion of the tube.
What's Q is the?
Q is the flow. So I'm going to use the letter Q to denote flow, right, with units length Q per time. And we'll work a little bit more with flow and velocity relationships in a moment. So if we have flow moving through these piezometers. No, not for steady flow, right? So these piezometers are stationary, but there's flow moving through the tube, right? So we have fluid dynamics in the tube, fluid dynamics in the piezometers. Be careful, everything's a tube. The flowing tube and the static tube, okay? So we can draw a streamline that runs along the center line, right? There's fluid flow that moves from this portion of the flowing tube to this portion of the flowing tube. And hopefully you can be convinced of that. We want to drop the streamline at the center line because it makes our assessment of the static pressure a little bit simpler, right? Because then we can describe a datum relative to a constant center line and describe the pressure at these 2 points as the height of these manometers, these piezometers. Okay. So if we were to apply this, we would probably want to start by looking for dropping a point 1 and dropping a point 2 along that center line, right below those piezometers. And that allows us to take advantage of the fact that we're measuring the static pressure of the fluid at those locations in those piezometers, right? And so if the elevation were changing in this example, right, we account for that by saying, well, in that example, Z1 and Z2 don't equal. In this example, Z1 equals Z2. But in either case, the static pressure is still the measurement of the piezometer, which is the specific weight of the fluid, times the height in that piezometer. Okay? So in this case, what do we have happening at point 1? Let's just denote the important terms. We have P1, B1, Z1, and P2, B2, Z2. So let's just review whether we think these are things we can ignore or cancel out or not. So at P1, is there static pressure at P1? Yes, right? I mean, the manometer, the piezometer is telling us that there is. So this is equal to some number. We have velocity at point 1. Yes, yeah, it's a flowing fluid, there's velocity. What about Z1? Talked about putting our datum right here. Z equals 0, define this as positive Z.
0.
Right, yeah, we'll call it 0, it's on our datum, right? If for whatever reason you put the datum somewhere else, then Z1 would not be explicitly 0, but what's important about Bernoulli is what's changing from point 1 to point 2. In that case, Z1 and Z2 would have the same value, you'd end up with the same endpoint, right? So Z1 and Z2 are 0. In this case, we have the same thing occurring at point 2 where we have static pressure and velocity.
P1 must be equal to P2, right?
Well, it depends on the elevations of the manometers that are given.
How do we define static pressure? Because in this case we have flow, right?
Mhm.
So we're saying there could be some static pressure even though there is flow.
Yeah, so essentially what's happening, right, is that we're moving, well, you'll see this, I think as you start to work examples, you see how the Bernoulli equation accounts for the change, the trade-off essentially of static pressure at point 1 for velocity head at point 2, or dynamic pressure at point 2, right? So what we need to do is, our assumption is that the density of the fluid can't change. So in this example, we have Q entering has to be the same as Q leaving, right? So we can't change the flow rate because our assumptions of the Bernoulli equation. The only way to move the same amount of flow through the part downstream of constriction is to increase the velocity, right? And that increase in the velocity, the energy to make that change has to come from somewhere, and it comes from the static pressure embodied in the fluid in point 1. So what's happening here is, we're getting a little bit ahead of ourselves, but these are great questions, because these are the sort of thought exercises that will make the application of the Bernoulli equation a lot simpler if you sort of physically understand what we're talking about. So to see that, realize that increase in dynamic pressure, it comes at an expense of a change in static pressure. Okay? Yeah.
So at point 1, we would expect the static pressure to be higher than point 2.
Correct.
Seems a little unintuitive to me, but
I think we worked through some problems, and I think you'll see that it sort of has to be that way for it to be equal to a constant along a stream line, right? Because let's look back to the Bernoulli equation here, right? Let's rewrite it. Plus 1/2 rho E1 squared plus gamma Z1 is equal to P2 plus 1/2 rho V2 squared plus gamma. And these two things have to equal one another. So Z's cancel, right? And we're left with P1 minus P2 is equal to 1/2 rho V2 squared minus 1/2 rho V1 squared. Okay, so those two things have to equal one another. And again, we're sort of jumping ahead of ourselves here. My original intent here was just kind of talk through like pressure, velocity, elevation at each point, but this is great. I mean, this is exactly what you should be thinking about when you're applying the Bernoulli equation. So conceptually, we're on the same page, I hope, that Q can't change by the very sort of assumptions that we set forth in the Bernoulli equation derivation. to move Q through a smaller area, we have to increase the velocity of 2, right? So that means V2 is greater than V1, right? And if V2 is greater than V1, is the right-hand side of this equation positive or negative? Positive, right? So mathematically, we can prove that the pressure, the static pressure difference, static pressure, has to be positive. So that's kind of cool. What this equation is telling us sort of helps our conceptual understanding of the system. From point 1 to point 2, we're taking that static pressure, sort of spending that money, and in exchange, we're buying extra velocity. Okay? And so, if you set up these equations, you'll end up with, you set up the Bernoulli equation and solve through making these assumptions. If you can get to here, then you might be in one question, a homework question, you might be told to solve for the pressure drop, given some information about the velocities. What we can really do is take something else away and have you solve for something else. So if you can get to here, then I think you'll be really successful in solving Bernoulli problems. Okay, great. Let's do one more quick one. It's similar to what we looked at before, with one little wrinkle. So in this case, we have a tank with a nozzle that's oriented upward, that's creating, upward velocity of our free jet that causes it to rise in elevation to some height. Right? We can analyze this situation with the Bernoulli equation, but this is an example of where it's useful to break it into pieces. Right? And so, in this example, we could do just as we did before. Apply Bernoulli on a streamline from 1 to 2. Right? And we end up with a very similar, the same equation as we showed previously. But we can also then extend this, and we can evaluate a streamline along the unconfined flow from 2 to 3. So this is an example where it's it's sort of convenient to divide and conquer essentially, right? From 1 to 2, we can develop an expression to solve for the velocity of 2, which is simply the square root of 2gh. Knowing that velocity, so we know the velocity leaving the orifice, right? What you might be asked to solve for is the height of that jet of water. Right? So, what do we know about the pressure at point 2? Let's just go through velocity at point 2, 0 or not 0? Not 0. What about the pressure? 0. Where would you draw your data to solve the problem from 2 to 3? Yeah, you might draw it at 2, but it depends on what information you're given in the problem, right? But if you set it at 2, z would be equal to 0. Right? What's going on at point 3? What's the pressure at point 3?
0.
What's the elevation at point 3? Z3 minus Z2. You have to know something about that to solve for. Well, that's probably what you'd be solving for. What's the velocity at point 3? 0. Right? That's sort of the trick in this question, is acknowledging that the peak extent of this free flow, right, is going to expend its velocity in exchange for height. Right? So we can apply Bernoulli and get an approximation of what the height of that jet would be. Okay.
Would it be did we say density was different at 3 or not? We assume density was the same at point 3 and that
Yeah, we'd assume it's, for this problem, we'd assume it's the same. Yeah, or in this class, we'd assume it's the same. Okay, so we've essentially talked through this problem already. This is an example of, well, I guess it's a slight variation. The figure to the right shows the measurement of the static and stagnation pressure at 2 points that allows us to measure the velocity of the fluid. So this is, sort of a similar device to a pitot-static tube. In the book, you saw examples of pitot-static tubes that are all combined into sort of one neat device. But this relies on the same principle, right? At one point in the fluid, we measure the static pressure. At another point in the fluid, we measure the stagnation pressure, right? And the difference between those things can allow us to extract useful information about the fluid flow. So, again, we already sort of talked through this. Can fluid statics be used to assess this problem? Why or why not? This is sort of an in-between answer. It's, partially, right? So we can apply fluid statics to the manometers. Right, but we need fluid dynamics for the flowing tube. So some of these, sort of convenient points are set up for you. It's similar to the example we talked about previously. If you see sort of, like things that stand out in the graphic, it probably stands to reason that if there's, something attached to your fluid, it's probably a convenient point to drop a Bernoulli point, because you'll be able to get more information about the fluid at that point than you would, in between these two vertical tubes, right? So this problem helps you a little bit by sort of indicating points 1 and point 2 and some of the descriptors of the fluid at those points. And so at point 1, it tells us that at V1, the fluid has some velocity V, right? At point 2, where we dropped our second point for Bernoulli, we say that the velocity at point 2 is equal to 0, right? And this is the difference between a piezometer and a pitot tube, right? So the pitot tube at point 2 is open to the flow, right? So it allows flow to enter, and then after it reaches a steady state, at the entrance to that open tube, we can assume that the fluid is static up through that tube. Okay, so that's why at point 2 we can take the velocity to be equal to 0. Okay, so let's write our Bernoulli equation. Let's go through the steps again here. We're going to draw a streamline that connects 1 and 2. Right? We're going to set our datum to be equal to 0 at points 1 and 2, because that's a convenient thing to do. Then we don't need to worry about the elevation head of the points themselves. And then we're going to draw positive z direction. Okay? So if we write Bernoulli from point 1 to point 2, we can cancel some things, right? What can we say about P1? Should we cancel it?
Isn't it equal to P2? Is it equal to P2? No.
So remember at P2, physically what's happening is we're taking all of that velocity and turning it into static pressure. Right? So that P term is embodied by the elevation of those vertical tubes overlying our points. Right?
Physically, could you describe how that would happen? Like, so the fluid is in motion,
Yeah.
and then something happens, and then on the other side it's not in motion. Is that what you're saying?
I'm saying at point 2, there's no fluid velocity. Right? Because it's the entrance to an opening in which the fluid rises to a certain height and is therefore static at that point.
Gotcha.
So I'm not saying all throughout, this is why it's really important about where you drew the streamline, right? If I draw the streamline here, then I can't say that the velocity of 2 is 0, right? Because I'm not at the entrance to that stagnation tube, okay? Does that make sense to everyone? Yeah.
Would technically the streamline go around the opening?
So this is, let me be
That too?
more precise. So I'm gonna draw a streamline that connects 1 to 2, and yes, this is a stagnation point. So for the purpose of this problem, I've connected 1 to 2 in a physically, realistic way, right? I shouldn't have just quickly dashed that line through, because you're right, our streamline does not just power through that opening, you can't. So at that point, we end up with something similar to what would happen way back in our example here, right? In this image, there's a streamline that essentially dead ends on the object. There's no more velocity, it's not going anywhere. Right? So other streamlines, though, will sort of do something in between, right? They'll deflect, they'll exchange some pressure for a change in velocity, but at one sort of singular point for our analyses, we're taking there to be a point where all the velocity goes away and it gets changed over for pressure. Okay, good question. Okay, so at P1, the pressure is not 0. At V1, the velocity is not 0. At V1, the elevation based on our data was 0. At P2, the pressure is not 0, right? The velocity is 0, and the elevation is 0. So from this, we get P1 plus 1/2 rho V1 squared is equal to P2, right? And we can solve this for V1 is equal to 2 times P2 minus P1 divided by the density and all of that to the square to the 1/2 power. Okay, so that's our expression for the velocity V, which is the velocity at V1. Now the pressure, the static pressure at P2, right, what's the static pressure at P2? Gamma H, gamma big H, right? This is all a continuous fluid. The specific weight of this pink fluid, in the manometer, it's rising to some elevation H. Right? In P1, we can do the same thing. We have a different height, little h, right? So plug those in, and we develop an expression for the velocity as a function of the changing heights of those vertical heterostatic tubes. Okay. Let's see. So this next problem sort of bring in what I think is an interesting work of biology. So albatrosses, one of the fastest flying birds in the animal kingdom, have 2 long tubes that run along their beak. So you can see that sort of right here, right? Look at this handsome guy, good profile. So right there, they have this like kind of odd opening pointed in the sort of direction that their face is pointed, right? And it wasn't until relatively recently that I think biologists can sort of figure out what that's there for. And it literally it's a stagnation tube. The bird has evolved a biological stagnation tube that allows it to get a sense for the velocity of an incoming fluid, or its velocity relative to that fluid, right? So they can sense their velocity by way of measuring the pressure at the front of their beak. Okay, so this is an application that looks, or a Bernoulli equation application that sort of takes this premise and asks for you to first to develop the equation that describes the relationship between the albatross's speed and pressure at the beak, and then to put in some numbers and to calculate the range of pressures that this biological pressure sensor can detect. Yeah.
Does our Bernoulli equation still work for gases because we're incompressible?
Yeah, right. Which obviously in this case is a more limiting assumption because gases tend to compress at a much lower range of pressures. But if you get a problem that's not sort of explicitly told that you should assume it's an incompressible fluid, then you can go and assume that gas is an incompressible fluid. Okay? So, the sort of premise of this problem is we got this bird, and it requires a bit of a simplifying assumption, but I think it's an interesting example enough that it's worth making that assumption, sort of talking through it. Right? So, the bird is, let's assume that it's, the bird is obviously flying into the wind, it's propelling itself forward, but for the purposes of the math of this problem, let's sort of flip that on its head and take the equivalent scenario where the bird is stationary and there's a flow flowing over the bird. Sort of just makes the math and the signs work out a little bit more conveniently. This is the same concept that if people do wind tunnel testing, right? If you want to develop an understanding of the range of pressures across the face of a building, right? You could either build a building and wait for the fluid to flow on that building, or you could construct a more convenient scenario. Probably a more relevant example is like a vehicle, right? You either drive the vehicle and sort of see how it behaves aerodynamically. That would be expensive and sort of difficult to control. Or you could put the vehicle in a wind tunnel and move the fluid and take the vehicle to be stationary, right? So let's take that assumption here. We've got a stationary bird. But we have the fluid moving at some velocity. So, similar to our previous example, what we can do is say that there's a streamline that connects the bulk fluid with a point just upstream of that stagnation point. Right. And if we draw a datum at z equals 0, this to be positive z, we can apply the Bernoulli equation 1 or 2. So P1 plus 1/2 rho V1 squared plus mz1. You'll be able to write this equation in your sleep by the time you're done with chapter 3. So this problem, if you look ahead, it asks you to solve with the range of pressures absolute. So let's go ahead and say that the pressure at 1 is not 0, but rather is 101 kilopascals. But you could solve this problem, gauge pressure, and call P1 0. What is the velocity at 1? V, right? So we can't get rid of that. What about the elevation at 1? Yeah, 0 from our datum. Okay, what about the pressure at 2?
Same as pressure at 1.
Not the same, but we don't know it, right? Pressure at 2 is what we want to solve for. We want to know what range of pressures this bird's biological stagnation tube can detect. So that would be what we're looking for, is the pressure at 2. Right? If you identify that this is a stagnation tube, then you can sort of look at the definition of the stagnation tube, or you can think through, what's happening in this scenario is that we have, essentially an opening to the fluid, and in that opening, we can assume that downstream of that, the fluid is static, right? It's entered sort of a chamber where the fluid is not flowing anymore. So that's the definition of a stagnation tube. So what's the velocity at point 2, just at the entrance to this bird's stagnation tube? 0. Yeah, exactly. And then the elevation? 0. Right. So we can solve for P2 then and create a relatively friendly equation that looks similar to what we just solved for, right? Okay, and I won't go through this next part. It essentially is putting some numbers to it. I'll provide, the sort of quick and dirty answer, but this is, from here, it's simply a matter of some unit conversion, but to sort of see what the end result is. So, let's ask for the range of pressures that the bird must be able to sense. So if the top speed is 100 kilometers per hour, again, we're assuming a stationary bird, and the equivalent scenario of it sitting there with 100 kilometers per hour wind, impinging on it. But if we want to look at the full range, then we could first calculate the pressure at point 2 at 0 kilometers per hour, which would equal what? The pressure of 1 plus 1/2 rho 0 squared, which is simply atmospheric pressure. Right? So as I mentioned, we'll solve this in absolute pressure. Atmospheric pressure, does anybody know off the top of their head? 101,000 and change Pascal. Okay, so that's the low range that the sensor needs to sense, right? Just ambient pressure. And then we can resolve this equation for P2 at 100 kilometers per hour, which essentially just requires a little bit of unit conversion and to know the density of our fluid, which is air. Right. So if you work through that, you should end up with 101,797 pascals. Okay. So the range of pressures, delta P, that this bird needs to sense is 101,325 pascals to 101,797 pascals. Cool, right? Albatrosses can do fluid mechanics. Okay, the next problem is actually, I want to make sure we have a chance to talk about some of the concepts that are in the next lecture. So we'll come back to that. Okay. Let's take 5 minutes though, since we've been going for a little while. We'll come back at 9.